This video is going to talk about pump power and how the equations for pump power are derived. It says centrifugal pumps up here because this sheet contains a lot of information specific to centrifugal pumps. But what we're about to talk about is generic, and this applies to any type of pump. So if we're trying to derive pump power and the equations that surround that, what we do is we start with a simple energy or power balance. So we draw a pump as our control volume, and then you draw your power coming in and your mass coming in and your power out and your mass out. So coming into the pump, we've got shaft power, which is what drives the pump. We have the liquid that comes in, that's to be pumped. And then coming out, we've got liquid, that same liquid's discharged at a higher pressure. And then we've got heat that's dissipated. So your shaft power plus your liquid power in has to equal your liquid power out plus your heat out. Now that looks simple. If you add up your outputs minus your inputs, it equals 0. What's a little more complex and what we're going to dive into is how much of that shaft power gets added into the liquid. And the power added to your liquid is also called hydraulic power. That's what we're going to dive deep into. A couple other useful equations here. Your efficiency of the pump is your hydraulic power divided by your shaft power from your motor. And then your heat dissipated is going to be equal to your shaft power minus your hydraulic power. That's to say whatever power from your pump shaft does not get added into your liquid has to be dissipated as heat. So let's dive into our hydraulic power equation. This here, the delta power of our liquid, so the change in power of the liquid, is equal to the total mass flow of the liquid times your delta or your change in all of these terms. And all these terms are representative of some form of energy. So U is internal energy. That's a function of the temperature of the liquid. PV, or your static pressure times specific volume, that represents the amount of power required to push the mass into or out of the control volume. It's also called flow work if you take your change in PV. Side note is internal energy plus PV is also called enthalpy. That's the definition of enthalpy. 1/2 V squared represents the kinetic energy of the fluid, which is a function of its velocity or how fast it's moving. Gz is gravitational acceleration constant times your elevation, z. And that represents your potential energy of the fluid based on how high up it is. So those are all the forms of energy that can be added to or taken away from the fluid. But with a pump, we can make some simplifying assumptions here. So this can become a much shorter equation. We can assume that delta U, or the change in internal energy, is 0 if it's a roughly constant temperature process. You can account for any temperature change later by assuming that the heat dissipation goes into the liquid instead of into the atmosphere. So that can be accounted for later, but for this equation, assume that the change in temperature is 0. We can assume the change in specific volume of the fluid is 0 because it's incompressible flow. With incompressible flow, your density of the fluid stays the same, so the change of specific volume stays the same. But your change in P times V is going to be different because from your in and out because your static pressure changes. But it simplifies it a lot that your change in specific volume is 0. Your change in velocity is either negligible or 0 because the amount of kinetic energy relative to your flow energy or your flow work energy is going to be very small. You could also say that your dynamic pressure, which is the pressure from the velocity of the fluid, is very small relative to static pressure. Sometimes you need to account for it for situations with low head and high flow, but generically you can say that's equal to 0. And then lastly, your change in elevation, or your delta Z term, is roughly negligible or 0 because the discharge elevation and your suction elevation is not going to be much of a difference, so you can ignore that term. By doing all those simplifications, your pump power equation simply boils down to hydraulic power is mass flow times change in static pressure times specific volume, and mass flow times specific volume is volumetric flow. So here's our final equation for pump power. Power added to the fluid is equal to your volumetric flow times your change in static pressure. And that's a really powerful and simple equation that we use for pumps. If you want to talk units, which is more practical thing to do and might help you make more sense of this. If we're dealing with imperial units, the most common unit we use for volumetric flow is gallons per minute, or GPM. The most common unit we use for pressure is PSI, or pounds per square inch. So if you take GPM times PSI, or your change in PSI, I should say, from outlet to inlet, GPM doesn't change. Your inlet GPM has to equal your outlet GPM because of conservation of mass. Take that product and then do some conversions. So convert your gallons to cubic feet, convert pounds per square inch to pounds per square foot, and that gets you in units of pound-feet per minute, which is a unit of power. And there are 33,000 of those in a horsepower. You end up getting this. Your hydraulic power of the fluid is equal to GPM times your change in PSI divided by 1714. And if you want to convert that to the amount of electrical power into your motor that's required to give you that hydraulic output, you simply take that equation above and divide it by your pump power and then divide by your motor power. And the product of those we call wire-to-water efficiency, which is the efficiency from your electricity that goes into your motor to the power that ultimately ends up being added into your liquid. I like this equation the best. I use this all the time because on site we see flow meters measuring GPM, we got pressure gauges measuring PSI, and we don't have to deal with specific gravity or density of fluids at all. So that's where this is a super useful equation. Now, pumps are often rated in terms of feet of head that they can add to a fluid. So if we're going to talk about this equation in terms of feet of head, we've got to do some different conversions to go from PSI to feet of head. So we'll do GPM times our delta in head added by the pump. Our conversions are going to be a little different here. We've got to convert density to slugs per cubic foot, and we'll talk about why we have to use slugs instead of pound mass and the difference between pound mass and pound feet in a minute here. But we convert density to slugs per cubic feet times gravity, 32.2 feet per second squared, convert gallons to cubic feet, and then we're back in this unit of pound force times feet per minute, 33,000 of those in a horsepower, and we ultimately get to this equation here. I took another step to show this in terms, instead of using density, using specific gravity. So ultimately this boils down to our hydraulic power equals gallons per minute times our change in feet of head times specific gravity of the fluid divided by 3,956. If you were to do this equation or this equation, you should get an identical number to your hydraulic power. And you can take this divided by that wire-to-water efficiency term here to get your electrical power going into your pump. Again, this is useful if you've got a pump nameplate or something where your pump's rated in terms of feet of head. And we'll talk about later when we discuss pump curves why feet of head is useful instead of PSI. So those are your two main equations you're going to have for pumps. Like I said, if you need to account for your velocity pressure, which is not accounted for here, you can do that by adding in mass flow times 1/2 v squared. Make sure your units are correct, but I think what you'll find if you do an example or two is that term is basically negligible almost all the time. But in case you do need to have it, or if you need to have your change in elevation of the pump or your change in temperature, it's all accounted for up here. I'd say 99% of the time though, use these equations and you're going to be good to go.